I now call to order the Society's 2,460th meeting in what is now the 151st year since its founding on March 13, 1871. Good evening, everyone. My name is Larry Milstein. I'm the president of PSW, one of the oldest scientific societies of Washington, D.C., dedicated to providing a forum to further scientific understanding and inquiry. Welcome to our members, friends, and guests to tonight's lecture by Charles Tahan of the White House Office of Science and Technology Policy. I am delighted that tonight's meeting is being held in person at the Cosmos Club, including a pre-lecture reception and dinner with our speaker. And it is being Zoomed as well. We plan to meet in person regularly going forward and to use Zoom and other social media when it's advantageous. Please check the website often for up-to-date information. We will be live streaming all meetings to YouTube for our remote audience to enjoy and to ask questions in the YouTube chat box. And final versions of the recordings will be posted to the PSW website and to the PSW YouTube and Vimeo channels, where they will be permanently available without charge for everyone. The Society is grateful to the sponsors of the 2021-2022 lecture series for their support, the Policy Studies Organization in cooperation with the American Public University, and a generous donor who asked to remain anonymous. We also want to thank the generous sponsor of tonight's lecture, PSW member Tim Thomas. He's back there. We'd all say thank you. Tim has been very generous and a long-standing supporter of the Society, and we're very grateful. If you're interested to sponsor a lecture or a series, please don't hesitate to let me know. I am pleased to announce the following new members. Lasse Svensson, Senior Program Manager, Engineer with Autoliv, North America. Interested in mechanical engineering, materials sciences, space technology and exploration, and renewable energy technologies, who learned of PSW through his wife and through PSW Special Projects Director, Cameo Lance. Robert Kiernan, a consultant with Kiernan Advisory Services, interested in superconductors and their applications, especially in maglev transportation systems, fusion energy R&D, and U.S. science and policy and competitiveness, who learned of PSW through the American Institute of Physics. Cindy Finkel, a physicist and data scientist with Booz Allen Hamilton, interested in fluid dynamics, quantum information sciences, and artificial intelligence, who learned of PSW through PSW Special Projects Director Robert Thompson. He's back there. Thank you, Robert. Conrad Bussman, Associate Superintendent, Materials Science and Technology Division, Naval Research Laboratory, interested in the physics of magnetism and magnetic materials at all scales, semiconductor technologies, and high-performance computing systems, as well as energy-efficient sensors, including quantum sensors, and the Internet of Things, who learned of PSW from PSW member Al Ehrlich, who's also in the audience. Thank you, Al. And Sofia Scarano, a quantum sciences researcher with Booz Allen Hamilton, interested in quantum circuit compilation, quantum machine learning, quantum utility benchmarking, quantum firmware, and ion trap hardware, who learned of PSW from PSW Special Projects Director Robert Thompson. Thank you again, Robert. And tonight's speaker, Charles Tahan, who learned of PSW from our invitation to him to speak tonight, and probably also from PSW member John Randall, sitting in the front. Thank you, John. Some of Charlie's interests will be clear from tonight's talk, and we welcome them all to membership. New members who ordered a PSW rosette can pick it up at the desk in the back of the room. If you're not a member and would like to join PSW or support the Society, you can do so most conveniently through the PSW website using the blue Join button at the upper right-hand corner of the homepage. We welcome new members and we appreciate donations. Recording Secretary James Heelan will now read the minutes of the 2459th meeting and the 91st Joseph Henry Lecture by Bob Ballaram on Ingenuity, the first controlled flying machine on Mars. James.
Thank you, Larry. Hi, good evening, everyone. On May 20th, 2022, from the Powell Auditorium at the Cosmos Club in Washington, D.C., President Larry Milstein called the 2459th meeting of the Society and 91st Joseph Henry Lecture to order at 8:06 p.m. Eastern Daylight Time. He welcomed new members, and the Director for Special Projects read the minutes of the previous meeting. President Milstein then introduced the speaker for the evening, J. Bob Ballaram, principal member of the staff at the Jet Propulsion Laboratory, California Institute of Technology, and chief engineer for the Ingenuity helicopter flown on Mars. His lecture was titled, Ingenuity, the first flying machine on Mars, first controlled powered flight on another planet. Ballaram's lecture told the story of the Ingenuity helicopter, which landed on Mars along with the Perseverance rover on February 18, 2021. Ingenuity made its first flight on Mars 2 months later, on April 19, 2021, with a piece of fabric from the original Wright brothers flyer on board. Mars's thin atmosphere presented the biggest challenge to engineering Ingenuity's flight. To illustrate, 1 cubic meter of air on Earth's surface weighs around 1 kilogram, while the same volume of air on Mars weighs between 15 and 18 grams, and is equivalent to the atmosphere of 100,000 feet above the Earth. Ingenuity also needed to be both a spacecraft to get to Mars and an aircraft to fly there. That meant the helicopter needed to survive the significant G-forces and vibrations it would experience traveling in space, without compromising its mechanical functions. It then needed operational autonomy on the surface of Mars, because the there and back again communications with Earth took 20 minutes. For the trip to Mars, Ingenuity also needed to stay out of the way. Ballaram said the helicopter was first conceived as a technology demonstration, and the personnel working on the multi-billion-dollar rover mission initially perceived the helicopter as a distraction. Ballaram walked the audience through Integrity's technical elements. The helicopter has 2 sets of airfoils mounted on the same shaft. The airfoils are 1.2 meters from tip to tip and spin in opposite directions at 2,400 rotations per minute. The helicopter weighs a total of 1.8 kilograms and operates around 350 watts. It is powered by a lithium-ion battery pack that is charged daily via solar panel and is capable of supporting 500 watts of power under normal circumstances. Ballaram described the unique techniques and materials his team used to keep Ingenuity lightweight and energy efficient. As Ingenuity flies, it takes 30 images of the ground per second to determine its velocity and runs control loops of its stabilizing sensors 500 times per second. It operates on open source F-prime software to run a smartphone processor 2 orders of magnitude more powerful than the Perseverance rover's processor. Ballaram showed videos of Ingenuity's test flights and described the technological challenges his team overcame throughout the development process. To mimic Mars conditions, the team constructed a wind tunnel made of 960 computer fans and tested Ingenuity's stability in an upside-down orientation. After several changes over the course of development, Ingenuity traveled to Mars attached to the belly of the Perseverance rover. It was covered by a debris shield to protect it during landing. Since landing, Ingenuity has benefited from its aggressive thermal design. It has multiple internal radiation baffles, high absorptivity coating for thermal energy harvesting, and CO2 gas gap insulation. The helicopter was designed to use 60% of its energy budget to running heaters throughout the night to keep the batteries at a warm -20 degrees Celsius. Now that Ingenuity is beyond its scheduled mission, it has been experiencing Martian winter and going down to -90 degrees Celsius every night. Ballaram said that, like Lazarus, the helicopter wakes up every morning and realizes it's on Mars. Ballaram showed imagery and videos documenting Ingenuity's landing and deployment on the Mars surface, equipment testing, and its first flight as captured by the rover. He then described Ingenuity's subsequent flights, and the complementary science. For example, Ingenuity's low-altitude surveillance allows for three-dimensional terrain reconstruction to help rover operators decide their best routes for surface exploration. The speaker then answered questions from the in-person and online viewing audience. One member asked about Ingenuity's lifespan, and Balaram said the helicopter's metal is the only inherently life-limiting item in the system. After approximately 200 landings, Balaram said the yield capability of the metal could drop. Another member asked about the maximum flight time. The speaker said Ingenuity now flies for almost 3-minute stretches and is limited by the motor's thermal limits. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. President Milstein adjourned the meeting at 9:53 p.m. The temperature in Washington, D.C., 30 degrees Celsius. The weather was partly cloudy, and the number of in-person and live online viewers was 87. The number of views on the PSW Science YouTube and Vimeo channels in the first 2 weeks of the lecture, 404. Respectfully submitted, James Heelan, Recording Secretary.
And so we now turn to tonight's speaker, Charles Tahan, and his lecture on quantum information science and quantum computing. Charles is the Assistant Director for Quantum Information Science and the Director of the National Quantum Coordination Office within the White House Office of Science and Technology Policy, where he is on detail from NSA's Laboratory for Physical Sciences. In addition, he is continuing to serve LPS as Chief Scientist and Director of the LPS Qubit Collaboratory. Previously, he served as Chief Technical Consultant for Quantum Information Science and Technology Programs in DARPA's Microsystems Technology Office. As Technical Director of LPS, Charlie drives progress on future information technology, standing up research initiatives in silicon and superconducting, quantum computing, quantum characterization, verification and validation, qubit science, and qubit technology. Among other honors and awards, Charlie's work has been recognized by a Researcher of the Year Award and a Presidential Early Career Award for Scientists and Engineers, and he is an elected fellow of the American Physical Society and an ODNI Science and Technology Fellow. Charlie earned a Bachelor's of Science in Physics and Computer Science at the College of William and Mary, and a PhD in Physics at the University of Wisconsin-Madison. All questions will be fielded after the lecture during the Q&A session. Charlie, the stage is yours.
I'm going to talk to you today about a lot of my career's work, quantum computing and the associated policy issues and other implications. Larry tells me that this is a very technical audience, so I made the talk technical. It's about our research and our progress towards realizing quantum computers. But I want to start with why quantum information science matters. And I want to end with some of the policy and strategy considerations that we think about in the National Quantum Coordination Office at the White House. There's a good argument to be made that without quantum mechanics, we wouldn't have computing and communications as we know it. The transistor, the laser, magnetic resonance imaging, magnetic storage, all these things wouldn't have been invented without understanding of quantum physics, and in particular, the more benign aspects of quantum physics, that there are atoms, that atoms have discrete energy levels, that there are particles like electrons and photons. In other words, quantum, the quantum piece of quantum. Having made these physical devices like transistors, which were based on these laws of quantum physics, humans formed abstractions. We made computers, we made programming languages to run on those computers. We devised a theory, information theory or computer science, zeros and ones, like the theory of zeros and ones, to help abstract and design more and more complex systems. All that works great, except that it's wrong, right? The actual laws of the universe are based on quantum mechanics. And we forgot that for a long time, but in the 80s, people started to ask questions like this. And if you're a physicist, the question started from this line of reasoning. If I want to calculate the properties of a molecule, like caffeine, or the properties of a material, like silicon, I write down a matrix that describes the quantum Hamiltonian, or the quantum dynamics. And if I want to calculate that matrix on a computer, a normal computer, I quickly realize that every time I add a particle or a degree of freedom, the matrix doubles in size. And I have to do tricks to try to figure that out, because now it's growing exponentially every time I add a degree of freedom, or an orbital, or another particle. And so people started to ask, and this is a picture of Richard Feynman, who gets too many credit for too many things, but he gave a lecture on this topic in the 80s, and he asked, well, if I had a computer that was based not on zeros and ones, but on quantum physics, the laws of the universe, wouldn't it be able to solve this problem easier? And that was the foundation of quantum computing, what a quantum computer is. Can you build a system that can simulate how the universe really works? Because obviously nature knows how to make materials work, right? It doesn't have to compute anything, they just work. So if you can build a computer that could simulate that, it should be more efficient for certain types of problems, especially the ones physics people care about. So over the last 20, 30, 40 years, a new language, a new perspective on information science and even physics has come about. In Quantum 1.0, people like Niels Bohr, Heisenberg, Einstein, most of the discussion was around particles, discrete energy levels, atoms, photons, electrons. That led to electronics, photonics, lasers. In Quantum 2.0, the language is about information science. And it's about thinking of bits or their analog, quantum bits, and how those manifest interesting things based on these kind of overlooked properties of quantum mechanics, things we'll call superposition, entanglement, quantum measurements. If you don't know what those are, I'm going to tell you about them as we go through the talk, but they promise disruptive new types of sensors and networks and computers. And quantum information science really is a foundational shift in information technology. To me, when I say that, it means this understanding is going to have transformative impacts on a lot of different fields in ways we still can't predict, even after 20, 30 years of thinking about it. It's still a very new field. And there's no better example of that than a large-scale, high-quality quantum computer. We have a few examples now of specific problems where a quantum computer can dramatically, exponentially outperform any classical computer you can think of. And this person in the middle of this picture is Peter Shor. In 1993, as a mathematician at AT&T, he came up with a quantum factoring algorithm, the famous Shor's quantum algorithm. And this predicted that if you could build a quantum computer big enough, you could factor very large numbers. And it turns out factoring large numbers is really hard. And it's the basis of our what's called public key cryptography, the networking protocols that secure our communications, everything from the president's communications to your financial transactions. So obviously, people got interested in quantum computing, and it became not a foundations of quantum physics discussion, it became a practical discussion of, is this possible? Can you build one? And when is it going to happen? Because much of our financial communications, secure communications, are based on this hard problem, which seems to be completely exploited by a quantum computer. And the best estimates right now are that if you could build a computer of about 10 million to 100 million physical qubits, and we'll get into what that means, you could break public key cryptography. Whereas, if you try to do that with a classical computer, it might take 1 billion years. So that's what I mean by exponential speed up. It truly dramatically is better. But there are other problems. So that's the first killer app, right? But it's not economically useful unless you're a criminal, right? There are other problems that we hope will be relevant. One is just the science question. Can we explore quantum mechanics better? And maybe the best argument for that is, if I take 50 qubits and I try to simulate that on my classical computer, I can't do it. No matter how big a computer I buy, purchase, or get access to, I can't simulate 50 perfect qubits and all their dynamics. So there's something beyond that kind of range, around 50, beyond 100, maybe to 1,000, where we're probably going to learn something new about quantum mechanics if we had such a machine. But keep in mind, that's perfect qubits. I'm going to tell you about that, what that means in a second. And then on the right side, there are problems, we think, in chemistry and material science. This is the original motivation that, if you had such a large-scale quantum computer, it would be economically useful. In other words, if somebody gave you this type of quantum computer, you would figure out a way to make money, either designing a better type of fertilizer, a new drug, and so on. But that's still very much a research question of how big a computer you need. So I've thrown a lot of words, physical qubits, logical qubits, operations. Now I'm going to tell you what all they mean in an example of how you would build such a machine. Okay. So these days, I have 2 jobs, and a big portion of them is workforce development, actually. We need a lot of people in this field of very deep, hard tech, microelectronics, quantum physics, electrical engineering, mechanical engineering. So I'm always trying to make every talk I have a career talk. And there are really many ways you can contribute to quantum, as a research scientist, as a program manager funding R&D programs around the country, putting a team together, and in policy. I'm going to give you examples of those as we go from my career. Okay, let's start with qubits. What's a qubit, or a quantum bit? At its simplest mathematical level, a qubit is just a 2-level atom. We could label the lowest state 0 and the upper state 1, and we can call that a way to store information. So if you're in the bottom state, you're 0. If you're in the top state, you're in a 1. I don't know how to use the pointer. I haven't figured that out yet. The top one, here. This is a 0 and 1. But it's quantum mechanical, meaning that if I shoot in radiation at the difference in frequency between 0 and 1, I can drive transitions between them, but I could stop halfway. And because it's quantum mechanical, it can truly be in a superposition of 0 and 1. This is where the quantum bit comes from. That's one core feature of a qubit. The other is that they're analog, that I think of a qubit as 2 complex numbers, azimuth and an angle. And I can point in any direction based on the phase and the amplitude of the microwave signal I drive it with. So these things are delicate, right? They're intrinsically analog. And because of that, that helps you store more information, but it makes them harder to control. The other thing, the weird thing of quantum mechanics you need to know is when you measure it, when you actually look at this qubit, even though it might be in a superposition of 0 and 1, when you measure it, I only get 0 or 1, always, with some probability given by the quantum amplitudes. That takes away a lot of stuff because it makes actually doing quantum computation much more difficult. You only ever get classical information out of a quantum system. And the third thing you need to know about quantum mechanics, and really this is all you need to know actually about quantum mechanics pretty much to understand quantum computers, is that as I add more and more qubits together, this is 3 qubits, the size of the space grows exponentially as 2 to the n. So 3 qubits has an 8-dimensional, 8-vector space. And you can have superpositions of all those numbers. So 2 to 3 numbers can be in superposition at any one time. And the fourth thing, if you just want to understand computation, is that you think of a computation as I have a number of qubits, I perform operations on them, and then I measure them. So I'm going to walk you through this as we go. This is my mental model of a quantum computer. I mean, we have a lot of bad analogies in physics because quantum mechanics is not an intuitive thing you grow up with, right? Like gravity. You practice gravity all the time because you fall 1,000 times as a kid, right? But quantum mechanics you don't see. It happens at the nanoscale or the microscale. This is my mental model, and that's just a mathematical matrix. 1 qubit is a 2 by 2 matrix. The classical parts are on the diagonal, 0 and 1. 2 qubits is a 2 to the 2 by 2 to the 2 by 2 to the 2, 4 by 4 matrix. Again, the classical bits that you can measure are on the diagonal. And then it grows like that, exponentially. 3 qubits is an 8 by 8 matrix. The quantum pieces are everything off the diagonal. Those are the superpositions. The magnitude of them, which can be a complex number, positive or negative, captures the extra information a quantum computer can hold. So if you think about how the quantum computation evolves compared to a classical computation, the classical computer is on the right. I don't have all these extra quantum coherences. The quantum computer has all this extra space. We call this the Hilbert space. And what happens during a computation is that all the space is explored. You fill up the information of many, many different paths. They can interfere with each other as the computation is happening because they have negative numbers. And at the end of the day, it collapses into the measurement. But the key thing here, and what I mentioned before, is perfect. In real life, qubits are not perfect. What happens in the meantime is that things like temperature, noise, heat, bad user design, bad pulses, screw up these coherences. And the worse those errors are, the more classical your quantum computer gets. So you're constantly fighting decoherence, which is basically making all these quantum coherence off-diagonal elements 0. And it turns into a classical computer. But at the end, you just get a classical result. So there's some magic that happens in a quantum algorithm, which is why there aren't that many. It's really hard to design them, because you need to design something where the answer comes into only these n bits that you can access. So that's my mental model. There's no perfect mental model, but that's sort of how I think about it. Okay, so once you have this mathematical concept of a quantum computer, and you convince yourself that I want to try to build one, you need to pick how. So if you think back to the 1940s, there was the vacuum tube, there was transistors, there's a lot of types of different options of logic before silicon CMOS was discovered. And we're very much still in that time, even after 20 years. There are many different ways to realize this two-level system. There are the atomic physics approaches, single atoms, and using those two levels. There are making artificial atoms and superconductors and semiconductors. And there's even more exotic approaches using photons that don't like to talk to each other or be confined, but can be good qubits, or even topological quantum many-body states, which are exotic forms of matter, which may have good properties for computing. I'm going to tell you about 2 types today, and the merger of those two, superconducting circuits and electrons, which are kind of very analogous to how modern day fabrication of computer chips looks like. Okay, so here's how we think about the quantum challenge. You've got a problem. Somebody tells you, I want to calculate the dynamics of nitrogenase, like the fertilization process. So you go to the quantum algorithm zoo, they tell you which paper to look at, you read the paper, it's too confusing, you just look at the number of operations you need to make the algorithm work. So just like any algorithm, you need to run some series of operations on your data. Your data are the qubits. Right? If you look at the paper, it says you need about 10 to the 14 operations to have any probability of success of answering the question you want. And quantum computers are inherently probabilistic. It comes down to this measurement issue. So let's say I want to have a 90% chance of success. I plug 0.9 into this sort of back of the envelope equation, and I'm solving for the logical error rate I need. So how good does each of these operations have to be if I want to have a large chance of success by the end? If I have to do 10 to the 14 operations, the error rate has to be around 10 to the minus 14. So one time out of 10 to the 14, it'll fail, and then your whole computation is dead. Another key part about quantum computing is that there is no copying, so you can't go restart halfway through. It's one of the weird effects of quantum mechanics. So all the operations have to work. So I need an error rate of 10 to the minus 14 for this quantum computer to work. I go back to my qubits and I ask, well, what's the error rate of a quantum operation on a qubit? So if I want to go from 0 to 1, and I do that by shooting a microwave for exactly a nanosecond on my atom, I'll find out quickly that the probability of error is something like 99% fidelity or 99.9%. So 1% error or 0.01% error. So that's a big gap. It's like 10 to the 12 orders of magnitude difference between what we can do today in the lab and what we really need to do something useful. So how do you bridge that gap? You bridge that with quantum error correction, which I'm not going to talk about. That's another website you go to, and you say, well, I need a quantum error correcting code that converts a whole bunch of physical qubits into a logical qubit. So what will happen at the end of the day is that these two things, the algorithm specification and the error correction choice, will tell you that if I need 1,000 logical qubits, each one of those logical qubits will have to be made up by 100 physical qubits, or 1,000, or 10,000. And you quickly get into the millions, 10 millions, 100 millions, billions of physical qubits to do your computation. Okay, so if you compare that back of the envelope calculation to where we are, over the last 25 years, we've come a long way. And indeed, on the right side here, I'm just showing there's a huge field of quantum information science that I'm not telling you anything about. I'm just telling you about quantum computing. I'm not talking about quantum sensing or networking or the theory of quantum information science or any of these other things. There's a huge field that's been developed. But if you look at the progress on qubits, it's been slow and steady, hard fought. Since Shor's algorithm, really the first major funding for the development of qubits, and we had no idea where we were starting, right, what to start with, came around 2000 by some of the big funding agencies in the US. By 2010, there were some good demonstration of qubits, meaning when I say good, I mean you build it and it works, because most of the time they don't work at all. You had 2 qubit gates, so you could entangle or couple 2 qubits. And then VC money, big IT companies started to invest or buy out academic groups and start to integrate these qubits into small arrays. And now we're at about 50 to 100 qubits with a fidelity of about 99%, so 1% error, approaching 0.1% error. So progress, but that's over 25 years. Okay, let's compare that to, so why is there only 50 qubits after 20 years, right? Let's compare that to, the modern miracle that's in your laptop, right? I have a MacBook. It's got an Apple Silicon M1 chip that has 16 billion transistors. They all work. Virtually all of them work. Why is that? One, the manufacturing is amazing, and we've had 50, 70 years to build that up, but that's not the reason. The reason is we have something called digital logic, right? And digital logic says that if my voltage choices are between 0 and 1 volt, I'm going to call everything between 0 and 0.3 volts 0, and everything between 0.7 and 1 volt 1. And so if there's a little bit of noise or a lot of noise, it doesn't matter. If I got 0.35 or 0.2 or 0.1, it's all 0. And if it's, same on the other side, I get 1. So there's a lot of leeway for errors, right? And the error rate of a transistor is something, I forget it, it's something absurd, like 10 to the minus 20, 10 to the minus 30. They're ridiculously good, right? That's one thing. The other thing that makes it easy, and I say easy after 70 years of this amazing economic engine of Moore's Law, the other thing that makes it easy is the interconnect. If you take the other side, it took me a while of searching the internet to find the backside of an Apple Silicon M1 chip, you can look at all the contact pads that are connecting it with the world. And if you count them, it seems like there's about 3,000. So 3,000 wires to 16 billion transistors. Think about the ratio, the mux ratio between that. That's what makes it possible or easier to do computing, because that mux ratio, having to have 16 billion wires would be really hard. But that turns out what you need for quantum computing. And the reason is that every qubit is its own delicate little flower. Remember when I said it's analog? You really need to touch those qubits and manipulate them a lot, all the time. And you need to measure them all, right? So every one of them, to first order, needs a wire or a laser or something to manipulate it and to read it out. And you can mux it to 10 or 1 to the 10 or 1 to the 100, but that only gets you so far, and there's a cost because then you're not touching it as often. And if you want to do error correction, you really need to recycle them. So that interconnect problem is just as hard as finding the good qubit problem. So we've been spending a lot of time on the qubit problem, but ultimately, we need a lot of qubits, and the qubits are not going to get to be 10 to the minus 12 good. You need a lot of wires. You need to solve that problem. And it gets better, right? Because not only do you need those two things, you need to do that all typically in a refrigerator that can get to 20 millikelvin, 20 times colder than space, or extremely high vacuum for the atomic qubits. And you need to do that within a power budget where that refrigerator can only handle so many watts of power dissipation. So there's a big holistic problem that you have to solve where typically making one thing better makes everything else worse. And so we're going to talk about that. This picture on the right is the inside of a dilution refrigerator where each stage, each circular pizza thing is a different temperature as you go down in temperature. Okay, so there's a whole zoo of qubits. I'm interested in the solid state ones. That's what I'm going to talk about. And I like them because they can take advantage of the manufacturing infrastructure that we've already built up for CMOS electronics. And most of my work is trying to make the qubits simpler, because simpler, I think, leads to better when you're trying to design a quantum computer. Okay, so the first qubit I'm going to tell you about are spin qubits. And these are the most analogous to the MOSFET, or the field effect transistor, in your computer. Here we have a single electron, this blue blob, with a spin. The electron has a charge and it has a spin 1/2. It could be up or down. That little magnetic moment you can use to encode information. You can call that your qubit. It can be up, down, it can be in a superposition. We trap it in a box. The box is made of silicon and silicon germanium, which have slightly different band gaps. And this thing, miraculously, the same material that we've used to build classical computers also appears to be very good for quantum, because the silicon you can isotopically enrich. You can get rid of the nuclei that are non-spin zero, and that's the dominant decoherence mechanism. The other thing you can do is you can push the dielectric, the oxides, as far away as possible, and that limits the charge noise, which again affects the qubits. Qubits are affected by everything. The whole goal is to isolate them. The other miracle thing about spins, single electrons, is that they're fermions. So if you take two electron wave functions and you overlap them with each other, by the Pauli exclusion principle, they evolve. They don't necessarily like that. So it's just like going from hydrogen to helium. You can use that to do an entangling gate. So it turns out practically that if you overlap them with each other just a little bit, within a nanosecond you can do a controlled NOT gate, which is the foundation of a quantum computer. That single reaction is really nice because it's also extremely on-off. It has extremely high on-off ratio, meaning when I bring them apart, they really don't interact with each other. And that makes scaling up easier. They're also really small, about 20 nanometers across. You can fit a lot of them on a chip. This is what PowerPoint engineering will do for you when you're trying to build a quantum computer. If you look at the bottom, this is a top-down view of a silicon quantum dot chip. Each of the blue dots is an electron. The lighter blue ones are being forced to overlap with each other. The gates, or the metal wires, are what control the voltage. Changing the voltage of those moves the electrons around. And another nice property of silicon is that the spin and the charge are decoupled, so that I can move the electrons by their charge, but the spin information stays preserved. So the quantum part is safe, but I can move them around to manipulate them. And then readout is done by another dot charge sensor. It's done typically by converting the spin to charge. I'll tell you about how that works in a second. The pictures on the top are pictures of real devices. On the top right here, you have a TEM image of a silicon-silicon germanium box, which is trapping the electron in the silicon quantum well in the middle there. And the other is a top-down image of an older style quantum dot device. Okay, so since their proposal till now is 24 years. And we still believe that they're special, even though the progress has been hard fought. The picture on the right is one of the coolest, more recent experiments. This is a 6-dot quantum dot array. On the top there are 6 dots with gates in between to allow you to tune the overlap between them. On the bottom are 2 charge sensors, 1 and 2, which act as single electron transistors to measure the spin to charge conversion. And on the right here, you see, this is from HRL Laboratories, the 6 dots are undergoing a dance. So it's sort of like a quantum abacus, where you're turning on these pulses, you're overlapping with each other to do 1 and 2 qubit gates, and this is time here, going in this dimension, and this is how your computation evolves. Actually, this is not a 6-dot quantum computer. It's actually a 2-qubit quantum computer, and what they've done is they've used only the exchange interaction and encoding a single encoded qubit into 3 physical dots. That turns out to be a nice property of exchange, simply because doing a single qubit operation of a spin via magnetic field is slow and has a lot of crosstalk. So if you do everything by the exchange interaction, you can actually make a faster quantum computer, but at the cost of more dots, 2 for 1 or 3 for 1, and more gates. Okay, so then that's what I'm going to talk, now I'm getting into the research part. Okay, so there's a zoo of, even within spin qubits, there's a zoo of different types of qubits. You can pick encodings of 3 spins, 1 spin, 2 spin, 4 spins. They all have different properties. Some have more immunity to noise, some are easier to control. And again, it's about this part of this holistic process of designing a quantum computer. So we were comparing ourselves with this encoded qubit approach that I just showed you, where you have pairwise interactions occurring in time. And we asked the question, well, if we have electron dots that are separate, couldn't we make molecules? Instead of single dots, what if I combine 2 or 3 and make them an always-on interaction, just like going from hydrogen to helium or to other more advanced atoms on the periodic table, and create a new molecule with new properties? Other people had this idea, but we found a regime where you can actually have immunity to charge noise, which is the shaking of electrons in the surface of your crystal, which is the dominant error source. You can have immunity to charge noise in fact, the 2 dimensions that matter, the tuning of the 3 dots and the tuning middle dot to outer dots. Those are the dominant sources of error. Further, a 2-qubit gate, instead of requiring 40 pulses, now just requires 1 pulse, because I have 2 like super spin qubits, which are physical qubits again, and not these encoded pairwise interactions. So that was a kind of a nice result, but it caused a problem, which is how do you read out these types of qubits? Because these qubits, these molecular types of qubits, we call the AN qubit, or a double sweet spot qubit, are almost too good in some respect. They don't couple to electric fields well at all. And you don't want to do this spin to charge conversion, which is the dominant and best way to do readout right now, because you destroy your qubit. So right now when people do spin readout, what they do is they use, again, these properties of fermions, that singlets like to go together, but triplets don't. So if you detune the 2 dots, if it's a singlet, it will go, but if it's triplet, it won't. So at the end of the day, if you have 1 electron here or 2, you can tell whether the qubit was in the 0 or the 1 state. The problem is you've now destroyed your dots, your electrons, you've lost them. You have to reload and initialize. You'd love a way to do that QND-like or quantum non-demolition-like, where the qubit is still a qubit at the end. And this is the way we came up with. It's revisiting what's called quantum capacitance. So if you plot, and now we're really getting into solid-state physics, but I'll try to help. If you plot the energy levels of your qubit as a function of the tuning, or the energy differences between your 2 dots, and now I'm just considering 2 dots, you get what's called a band diagram. And you call these 2 levels your qubit, a singlet state, just like in helium, and a triplet state. So singlet is up-down, minus down-up, triplet is up-up, for example. Those are your 2 qubit levels. If you think about what happens when you connect a wire to your dots, and the picture of the dots are 2 here, these 2 red blobs. If I connect a wire to one and hook it up to a tank circuit or an LC resonator, say at 500 megahertz, and I shoot down microwave or RF signal at 500 megahertz, what happens is that one of the dots starts to shake at 500 megahertz. And the electrons, and as a function of energy, the splitting will start to oscillate depending as a function of how much you're driving it. And you can see that the phase shift that comes back will depend on whether you're in a triplet state on the top or a singlet state on the bottom. The singlet state is actually more curved. That curvature is the quantum capacitance. So driving these dots at the resonator frequency enhances the signal and the difference between the triplet state and the singlet state, the 0 and 1 states, which you can now observe even in these really incredibly protected qubits. And we recently, that was all theoretical over a few years, we recently worked with Mark Erickson's group at the University of Wisconsin to show that this happens in practice, where if you, again, drive one dot at the resonator frequency, you get an enhancement of this quantum capacitive signal. Once you have that, you can start asking questions about, well, maybe this approach of just doing everything by exchange gates, maybe that's not the best way to do it. Now that we have a great measurement approach, which is 25 nanoseconds, and you can do in place, non-destructively, maybe you can design gates completely by measurements or with exchange and measurements, which were much more efficient. And so this was just the first step along that, where we showed you can reduce the number of dots and gates by a factor of 2 to 3 if you add in measurements. And we're getting into the details here, but there's in quantum computing land, there's a renewed interest in thinking about how variants of measurement-based quantum computing can be used to do all quantum computation. For example, in topological qubits, another variant that I mentioned earlier, they're naturally compatible with this longitudinal coupling we talked about. Also, it looks like if you can do joint measurements on qubits easily, you can come up with new error correcting codes which are much more efficient. And I'll just have you think that I've talked about these encoded qubits, where I have encoded one qubit into 2 physical or 3 physical dots. But if you measure a single triplet qubit or a 2-dot qubit, are you measuring 1 qubit, or are you entangling by measurement 2 separate dots? So you can play games now in this, because these are fermions, you can play games with how you think about whether you're doing a single measurement or a joint measurement. It's just a quite interesting area of research. Okay, I'm going to take a break. We're going to do questions at the end. Now I'm going to talk about a different type of qubit, and then I'm going to smash them together at the end. Okay, so another type of qubit which is extremely popular is the superconducting qubits. This is the type of qubit that Google, IBM, Amazon are all pursuing to build quantum computers and others. They're pretty cool. From a physicist's point of view, they're pretty cool because they are just wires on a chip. They're just electrical circuits. You happen to make those electrical circuits out of superconductors, but aluminum, if you take it down to 20 millikelvin, goes superconducting. So it's basically, there's like aluminum washers. That's it. You can think, if you're an electrical engineer, there's just LC circuits with a little bit of nonlinearity. And that nonlinearity comes from a Josephson junction, which is just inserting an insulator between 2 superconductors. That Josephson junction makes the artificial atom you're creating here anharmonic. And at the end of the day, you can think of it just like a spin or just like an atom. It's a 2-level system. Over the last 10, 15 years, people have come up with creative ways to protect these qubits from charge noise. They're just electric dipole moment qubits. It's kind of amazing they work at all. But people have come up with incredibly genius ways to make the energy levels of the qubits. This is called the transmon qubit energy diagram. So just call this bottom level 0 and this one 1. And you can see Ng is charge. As a function of charge, say there's electrons hopping around, nothing happens to that qubit energy. It's completely flat, which means that it's very robust against charge noise. Right, so these tend to be good qubits nowadays, almost 100 microseconds of coherence time, which is, believe me, is good. We started at nanosecond. Here's a picture of a little bit outdated IBM qubit chip. I think had 8 or 10 superconducting qubits. These are big, whereas the dot qubits I mentioned were 20 nanometers across. These are 100 micron to a millimeter. I mean, they're huge, right? But they're easy to make. It's a single layer of metal. They're big. You can use old style fab equipment, and they work. Every one you make works. Here's a picture of the Google quantum supremacy experiment that got a lot of headlines. We even invited the team to the White House. This is right before I started, who achieved quantum supremacy. This is on the right here, a 50 qubit chip with couplers in between them. And I'll just mention briefly, this is a good example of how a quantum computer works. On the left here, these things that look like X's are called Xmons. They're the qubits, variants of the transmon qubit. There are 5 of them. The couplers, A, B, C, and D, will let you do 2 qubit operations. And this thing on the right is just the time. So you start in some initial state, you operate on the qubits. The single qubits are operated on by microwave fields. The couplers let you do 2 qubit gates. These little boxes are each single qubit gates, and the couplers are these things that connect the wires. Each wire is a qubit, and at the end you measure. So they ran experiments like that on 50 qubits. And really the magic of this device, the thing that made it work, this is the biggest system that had worked so far, was the coupler. Because before then, there was never a way to turn off the coupling between all these qubits. So when you added more and more, it would just get more and more complicated. But the coupler, which was proposed by MIT and realized at Google, really allowed you to turn off the coupling. This is a 0 here. It's going to 0 at a certain tuning, and that lets you turn off all the coupling so you could calibrate and then run your algorithm. We took a little step along the direction of merging the good properties of superconducting qubits with the good properties of disseminating qubits. So the one complication of the Google approach is that each qubit needs a microwave generator. Microwave generators are big and expensive. You can make them smaller, they'll still be expensive. And if you want to make a lot of qubits, it's a big overhead. One thing that's nice about the spin-based exchange approach is that everything is done by baseband voltage pulses. So you don't need a microwave generator, which is a huge win. So we asked the question, well, could you design a superconducting computer that doesn't need microwaves? Save yourself a few $1 trillion if you want to build a computer. And we did that by proposing encoding. So instead of 1 qubit per qubit, you have 2, which encode 1 physical qubit. And then we showed how that could be realized by collaborating with MIT. The bottom here are 4 of these Xmon qubits, but each 2, they're in pairs. So this is 1 qubit, 1 pair, this is another. And we show that even without microwaves, you could have very high fidelity gates, 3 nines fidelity for single qubit gates, which is a nice stepping stone. And it comes to the crux of one of my areas of interest, which is how do you make both better by combining them? If you compare why silicon qubits are good, it's mostly because you can really make an epitaxial single crystal device where all the bad stuff is around the edge. This is the oxides and all the bad stuff. A superconducting device is huge and heterogeneous. There's bad stuff everywhere. The bad stuff is the qubit in a sense. So the qubit is made from these huge wires which have an oxide around them. The insulator itself is typically lossy. There's a substrate, there's whatever's on top. All that stuff screws up your qubit. So if you could really make an epitaxial qubit, potentially you could revolutionize how good they are. This is a picture of a superconductor aluminum grown on a 3,5 semiconductor. I think it's indium antimonide, for the purpose of topological qubits, but I'm just showing you the picture. This is a perfect crystalline growth of 2 different materials. So it's starting to show that that might be possible. And what's really amazing about this material is that the things that make these things superconductors, Cooper pairs, the pairs of electrons that make it go superconducting, can travel into the semiconductor and make the semiconductor go superconducting, but still retain some of its semiconducting properties. So it's gate tunable. You can hook it up to CMOS, not to flux. This is how you make them in a molecular epitaxy machine. We have one at LPS. This is from Chris Richardson's group. It's pretty cool. Here's some pictures of epitaxially grown Josephson junctions with traditional metals, aluminum nitride, niobium tinitride. And here's the idea we created them up with, which was pretty crazy, and maybe still is crazy, but we'll see. And the idea is, don't try to use different metals. Take a silicon crystal. If you could go inside and replace silicon atoms with say, boron or aluminum. It turns out that you can make the silicon go superconducting. And if you could do that completely epitaxially, you'd have a single crystalline superconducting device, which would be really small and really high fidelity. And that might seem insane, but people like John here and others do insane all the time. This is a picture of STM lithography where you've taken, we're looking down at the surface of silicon. You use a scanning tunneling microscope tip to pull out specific atoms and replace them with other atoms. And you can do that at the scale of 1 atom or the scale of nanometers. Then you can regrow silicon on top. And all our proposal was saying is if you could do that over a few layers over here on the right and replace some of those with boron or aluminum, it should go superconducting while maintaining its crystallinity. And if you could do that, and you can do 2 layers, you could make a transmon qubit like the X's I've been showing you, which are millimeter, 100 microns across. You could do that in 1 micron, and it would be better. So that's 1,000 times smaller than what your present state is. And now you can start to really think about a qubit chip with a lot of qubits on it, right? This same type of technology could be relevant for tunable kinetic inductance detectors, which are used for astronomy. Okay, so in fact, we started a whole program on it because it's such a fantastical, amazing, impossible problem. So you can imagine doing that in silicon. You can imagine using 2D materials like graphene and stacking them with different superconductors to make your capacitor. You can imagine doing other exotic things. It's really hard. We don't know if it will work, but if it does, it could potentially disrupt quantum computing. And that takes me into another way you can change and affect quantum, and that's to start an organization. So we at LPS launched the Qubit Collaboratory a couple years ago. That was in response to the National Quantum Initiative. The idea was to create a new kind of center where, one, we're focusing on these long, hard-term material science problems that could potentially make disruptive advances in quantum. The other was to focus on building the workforce, because now, when I got out of college, you wanted to do quantum computing, there was the government, there was universities. Now we're competing with Google, IBM, Microsoft, Amazon, VC companies. It's a lot of competition. We need more people to decide to go in the government. So one of the main focuses of this was to build the workforce, with some of them hopefully deciding to go into the government eventually. And the other was to actually form deep collaborative partnerships. So unlike other US government funding approaches, we don't ask for a proposal. We give you the problems, and we ask that you come and say, hey, I want to work on that too. And we will develop the proposal together. So it really is a collaboratory. And we picked a few research problems to put out first, and you've seen themes of them today. Spin qubits, how does epitaxy affect quantum computing? Can you do voltage-controlled CMOS-compatible superconducting qubits? Other ones are, can you make hot qubits? You don't need a fridge. Can you use the technology we're developing for classical computing? This is beyond more, before sure. And then also, can you speed up learning? One of the things we started was a Qubit Foundry. So instead of being a new professor and having to go out and buy $1 to $5 million of fab equipment, we will just give you the qubits. You send us a design, we'll go to Lincoln Labs or other companies, and we'll send you the qubits so you can do physics experiments and not have to worry about fab. It's not for everybody. We don't want everybody to not do fab, but it can make the field much more inclusive, right? Because you don't have to do all this stuff at the beginning. So this comes to one of my pet projects, which is, we know at the end of the day we're going to have to make quantum computer chips like we do Intel chips. We're going to have to fab all the wires on the same chip. But in the meantime, could we do something else more clever? And the idea is, could you separate the qubit chip, where the qubit actually lives, from all the control and stuff that makes the qubit? I call this, off-chip or induced dots. And the picture here is showing a chip that just induces the dots. So if you look at how quantum dots are made now, they're boxes in the z direction. And over time, we figured out how to simplify them. At the end of the day, it's just a box in z, where it traps the electron in the z direction. And one gate that's positively charged will trap it in the xy direction. That's your little egg carton box trapping an electron. So I could make that without fabbing. I could do that with an STM tip, for example. One wire that comes down that has a voltage, positive voltage. I can use that to trap my electron. This is the surface of some crystal. I've created a DC voltage on it, and then I've hooked it up to this tank circuit I was telling you about to do readout. So I can combine all these ideas into a novel way to induce a dot without actually having to fabricate it. You know, and me in my career, I've watched many, many graduate students spend 6 years just figuring out how to get rid of leakage, you know, before they even got into qubits. So if we can figure out a way to explore materials faster, that's a really big win. And so we're doing this at LPS with collaborators. It's India and Texas. This is a picture of the STM on the left, and it's scanning the surface of silicon and seeing what appear to be, this is very early data, you know, single dopants that have hybridized with this dot that we're creating. On the right is the next generation, creating a fully flipped chip integrated design, where you can switch out the bottom part and just keep the top part to make your dots. Okay, so we're rounding out the day, and this is the last topic of the science part. You can combine the two ideas. This is where it gets really cool. If you take a germanium quantum well, very similar to the silicon quantum well I just showed you, it will trap holes instead of electrons. The holes are like the opposite of electrons in silicon or germanium. Holes are interesting for quantum dots in their own right because they don't have, they're a gamma valley. They don't have direct band gap issues that plague silicon quantum computing. That's a more complicated issue. So you can make quantum dots out of them, and they're bigger because the effective mass is smaller. That makes it easier to make. So they're interesting for science for quantum dots. But what's more amazing is that if you deposit this red metal on top aluminum, it's strongly believed that this will proximitize the quantum well, meaning the Cooper pairs, electron pairs in the aluminum superconductor will go down into the quantum well and make the quantum well go superconducting, which you can then gate with a voltage. And if you can do that, you can make superconducting qubits, which instead of being controlled by flux or currents going through a wire are now controlled by voltage. And we have 50, 100 years of experience developing electronics that control voltage, you know, and we know how to scale that. So you can make transmon qubits. Here they look like T-mons, you know, where you've replaced this aluminum Josephson junction, aluminum oxide, aluminum Josephson junction with some kind of semiconductor, like a two-dimensional whole gas, or a nanowire, or a graphene. Those are called gate-mons. And if you can do it in germanium, it's particularly interesting. It's also very interesting for a theorist because now instead of a kind of a dumb Josephson junction, I can replace the junction with a dot or a quantum point contact or other symmetry physics-y things that could add new properties. And I'll just say, all that sounds great. There's a lot of hard problems to solve, one of which is when you grow this sample, there's a lot of loss in the graded buffer layer when you're creating this quantum well. And unlike dots, which are super tiny, you don't see it, superconducting qubits are huge. So the electric fields actually go down a long way into the substrate, and they see that loss and make your qubits bad. So what you typically have to do is etch away all this stuff, and then you have really long wires that go up to make your junction. So here's the final idea for the night. This is one we just published. And that is, instead of making superconducting qubits, which are planar, and I never told you why people make them like this. The reason they make them like this for qubits and for particle detectors for astronomy is that oxides are lossy. And so if you make them really big and wide, all the electric field goes into the vacuum and not into the oxides, right? So you see these huge things, you're like, why are they so huge? The reason they're so huge is because you're trying to get away from the actual material. If you could make a perfect material, they'd be small, right, as I said. So if you can't do that, do the next best thing and make them vertical. So the idea was just sort of like Darth Vader's ship, put the contact pads vertical and put them on a different chip. The chip on the top is the probe chip. That is pure silicon, which we know is extremely low loss. These are now through silicon vias, about 30 microns across, so pretty big compared to dots, but small compared to superconducting qubits. The green things are those pads. They're the X's that you saw before. The orange thing is the voltage control layer that allows you to tune the number of carriers or electrons or holes in your weak link junction, which lets you tune the frequency of the qubit. And these blue things are ground to shield it. So now what you've done is you turned this planar, really big XMON or transmon qubit into a 3D superconducting qubit, which has a super semi-junction, which is compatible with CMOS electronics. And in reality, if you do it to scale, it's 100 times smaller. You can fit 100 of them now in the same spot, which is, if it works, really cool, right? So we've done some simulations to show that the participation ratio of the energy coming from the lossy part is 10 times smaller, and indeed it should be at least 2-4 times better. And you can even do 2-qubit gates. And again, if you design special types of coupler qubits, you can get to these points where you have very large on-off ratio. And the super semi part helps you because you can really deplete all the carriers in that weak link. Okay, just to show you that it's not fantastical, here's some pictures of real devices, not of super semi qubits, but of flip chip superconducting qubit engineering that is done in Lincoln Labs. It's also done at many other places these days. Okay, so what do we have? We have now a replaceable qubit chip. I can use germanium if I want. I could use a 2D material like graphene. I could use gallium arsenide. I can play around with it. I have a voltage control compatible qubit. It's 10 times smaller. I can use it with dispersive readout like I told you about. I can use encoding to get rid of the microwave gates. I can have a true off. And I can add novel physics. And there's a lot of impossible problems now to solve. So for a physicist, this is a whole new system of qubits, which I'm excited about. Okay, that's the end of the science. And now I'm going to talk about the policy in the last 5 or so minutes. Okay, so I have the great honor to lead the National Quantum Initiative at the White House these days. So I want to tell you a little bit about that. The National Quantum Initiative Act was signed at the end of 2018. It created a bunch of coordinating bodies in the government. My office, the National Quantum Coordination Office, which has detailees from the major funding agencies. We now have DoD, NSA, NSF, NIST, DOE. It created 2 subcommittees on quantum, one civilian-led and one focused on the economic and security implications of quantum science. Because you see, right at the beginning, that cryptanalysis has always been a consideration of quantum computing. You always had to consider it. Created an advisory committee. And more importantly, it funded a whole bunch of new science. You know, about 13 new centers across the country. We have a national strategy. This was written by the 13 or 14 agencies who have equities in quantum. Here are the 6 pillars, you know, very much a science-first approach, but with workforce very closely behind. And also thinking about balancing this economic and security components and international cooperation. If you add up the numbers, about $1 billion a year in funding in the NQI. And this is what it's about. It's forming an ecosystem. You know, so we're trying to create a new field, right? You know, over the last 20 years, it's been bubbling up, supported by funding agencies. The last 5 or so companies have been getting in seriously, but there's still a lot of science to do, particularly in understanding what the applications of a quantum computer are, or quantum networks, or quantum sensors. And so a big part of it is the science, but another big part is education. I'll just point out, OSCP and NSF launched the Q12 Education Partnership. This is a consortia of the big companies, small companies, the teachers' associations in physics, to form curricula at all levels for education, also to run events like World Quantum Day, which we launched in April this past year. There's some great stuff on that site, profile videos of people in the field from different paths they've chosen. Also, links to quantum games, ways to teach people intuition about quantum computing, you know, without them knowing it, like quantum chess, or I'm in a game called Mechanic. A big part of the NQI Act was also the industry. So the Act called for NIST to set up a Quantum Economic Development Consortium. There are now about 170 organizations, 140 new companies, or old companies who are in quantum. You know, we're still at that point in quantum computing and quantum information science where you can count the number of companies. So it's an exciting time, and it's an opportunity to get things right. And especially in the context of protecting our intellectual property and working with these companies to help get their cyber awareness up and so on. You know, if I had to summarize the 3 objectives of this administration, you know, number 1, get the science right. So understand the applications that will make this field matter to people. Second is, you know, enhancing our competitiveness. You know, how do we work together with our friends and allies to protect the technology while moving it faster? And then 3, how do we enable our people? You know, 1 is opportunities for new jobs, but also how is it going to affect society and help people broadly? And if you're a scientist, I would look at this Quantum Frontiers report, which lays out what we think are the top 10, you know, challenges in the field. In the fall, we had an industry summit. We brought as many people as we could fit into the White House with the COVID restrictions to talk about some of these challenges. And, you know, we heard a lot of different opinions, of course, but, you know, some of the summary is, you know, there's a need to accelerate this technology while finding creative solutions to protect it beyond just export controls. But very different opinions on technologies, you know, whether quantum sensing will be the thing that matters or quantum computing. And, you know, if you just think about the application space, there's a lot of work to be done. You know, we strongly believe there's a scientific discovery to happen in the 100,000 and then, you know, like the 1,000 qubit range and beyond. We know that cryptanalysis is out there for a very big computer, but there's a lot of murkiness about the other applications, chemistry, material science. How big a computer do you really need for somebody to care, right? And what's the economic driver for that? That's a really important field, and we need more people looking at applications. Last couple things, international talent. You know, what happened in the last 2 years? COVID happened, it shut down shut down a lot of immigration. A presidential proclamation came out almost a year and a half ago, maybe 2 years ago now, stopping immigration from certain universities in China. You know, so there's a lot of concern that we were going to stop our seed corn, the talent that comes to this country that creates our scientific enterprise. The first report we wrote out of the Essex subcommittee was really around that question. How dependent are we on foreign talent? How important is it? How do we address this in a more competitive world? And then finally, the most relevant thing, which just came out exactly a month ago, presidential directive signed by President Biden, called a National Security Memorandum, which is basically like an executive order on quantum computing. It had 3 components, and I'm mentioning all these 3 because only one is usually mentioned in the press, which is we need to move to post-quantum cryptography. So if you had a quantum computer, you could break our encryption, you could steal our IP, you could steal all your money. You know, if we had that today, it'd be really bad if somebody had that. We luckily won't have that for a long time, but the government certainly, many companies are charged with protecting information for 25 years or more, right? So you need to move to cryptography that's resistant to a quantum computer now, because it takes a long time to do right. The other 2 parts that are really important are that there's promote part, where we have to focus on our science and our workforce development to lead the world. We have to keep that as a priority. And we need to figure out how to protect this technology in innovative ways. So it asks the agencies to actually develop technology protection plan. So why did we do it? 1, cryptanalytic scale quantum computer seems possible. Like there's no physics reasons we found yet. We might find some. It's really hard. I hope I've convinced you of that so far. But it seems possible. So you have to take it seriously if you're conservative about protecting your information. And we know that even cryptologic transitions that have happened in the past and gone well have taken at least 10 years. If they go badly, they never happen. So we're in the area of vulnerability now because people can save information and decrypt it later once a quantum computer arrives, if it does. So you need to take it seriously, both the economic and national security threat. And to move to PQC is going to be expensive and require a lot of coordination across government and with industry at all levels. So you really need to prescribe agency this, you need to do this now. You need to set a timeline, and that's what the NSM does. And then finally, this R&D investment needs to be protected, but it needs to be done in a thoughtful way, which doesn't slow down progress. And you need to think about it in a new world, you know. All right, so I'll just end with a happy note, which is the most recent event we had, which is bringing 12 countries together at the White House last month to talk about quantum cooperation. And this is, we talked about these 3 topics. It was actually a really great meeting because people were very happy to see each other in person. And given the events of the last 100 days, people are very keen now to work together. The petty squabbles of who's going to get rich on this thing matter much less than ensuring that we all are first together, right, as like-minded countries. So with that, I'll close and tell you just to look to quantum.gov if you're interested or want to find out more. And thank you again for having me.
So we have time for, I should say thank you, and we have time for questions. So let's start with question in the room. Okay, red microphone, go ahead.
Hi, my name is Frederica Dorima. I'm a PSW member. Thank you very much for this tour de force presentation. I must say I am really glad that you're heading the quantum computing initiative for the US and maybe the world. I have many questions, but I wanted to ask, in the technologies that you talked about, is it the decoherence problem addressed because now you use applied voltage control? One question. I have also some related questions. I'm glad also about this effort because it reminds me of your foundry, because it reminds me of the semiconductor consortium in the 70s that gave the impetus for the semiconductor technology. So I think this is a great direction. And also, you talked about, okay, I think Larry doesn't want us to ask multiple questions.
Question.
One question, 5 parts, right? So.
Question is, in a sense, to address the decoherence. Related to that, when you talked about how many qubits we need, it depends on the application, perhaps. So can you identify some important applications certainly that would make it that worthwhile?
Sure. So to the decoherence part, all the qubits have problems with decoherence. We've gotten to the point where single qubits are pretty good, and now the action is in the 2-qubit gates, which are most sensitive to noise. In the super semi-qubits specifically, they're still early days. They're about 10, 100 times worse than modern superconducting qubits, so they need to improve. But again, it's a holistic problem. So if you can have more qubits that are easier to make or easier to control, that might be worth it in the grand scheme of things. And I think they're actually going to get better too. To the foundry, actually the foundry idea has been tried several times in the history of quantum computing. Like quantum computing is in the news a lot today, but it's actually had several hype cycles over the last 20 years. The previous Qubit Foundry problem, Qubit foundries have failed because the qubits weren't good enough. We didn't know how to make them. Now there's a few certain type of qubit types, the superconducting ones, which actually all work. When you make them, they work. They might not be good, but they work. And so you can really send a design file to MIT or to a company and get back qubits that work. So that's working that well now because the technology has evolved enough such that it's no longer a researchy game, just getting them to work. Oh, the applications. I tried to hint at this at the beginning. So again, the numbers are still working, but if you take like proposals for understanding key pieces of the Haber process, it's projected, the estimates are something around 10 to the 14 to 10 to the 17 gates. So you need a big quantum computer, probably comparable to a quantum factoring machine for 2048 or 4096. So right now, however, there's a lot of heuristic algorithms that have been proposed at the 10,000 qubit range, 1,000 maybe, and we just cannot prove whether they'll work or not until you make it. I'm skeptical, but there's still a lot of hope. Certainly for science, there's going to be a lot of cool stuff coming out in the next 5 to 10 years.
Going to take a question from a Zoom participant, Bill Phillips. Bill, if you unmute your mic, you can ask your question, I believe.
First, Charlie, that was a great talk, just beautiful. As a number of people know, for almost 2 decades, I've been saying that there is about a 50% chance that we will have a quantum computer that can factor numbers that can't be factored by whatever classical computers we have at the time. And in spite of what I consider to be amazing progress in qubits, I still think that. And what I'm wondering is, what do you think? Am I being too optimistic, too pessimistic? What's your view?
I always hate it when you say that phrase. I think I'm going to give an answer that my wife loves to hear. It depends. I think the question should not be taking a random subset of the field. It's really asking experts. And I forget, Bill, is it 50% in 10 years, 50 years? What was it again? So I think let me put it this way, it doesn't really matter. I think there's a histogram, right, that's going out to 50 years. I think it's kind of dependent on the economics of whether it makes sense to keep building quantum computers. It may not be a technological thing, but I think you have to take seriously in the next 25 years, which is the length of time we need to protect information typically, and longer, that a quantum computer could happen. Either by advances in engineering and physics or by mathematical advances to bring that whole number down. So I think 25 years, within that range, there's a pretty good probability of something happening.
Go ahead.
Thank you. Excellent presentation, very informative for me and hopefully for most of us here in the audience. It sounds like this is in the Wild West stage where you have different materials that are being looked at, different methods. And my question is this really a technology problem or is it a coding problem, meaning hardware versus software, or where will it?
It's all of those problems. Yeah. Finish.
Which do you think is at this stage of the development? And I guess one question I have too is this a possible dead end? But if it isn't, what are the major technical hurdles at this point? And do we have the capability to interact with it, to program it?
Okay, a few different questions there. The first one is quantum information science broadly is not a dead end. It's a foundational technology. It matters today in sensing, clocks, other types of sensors are coming down the line. Quantum computers are tremendously scientifically interesting, no matter if they have any application. I think of them as, you're building a telescope where you can change the properties of the universe as you're using it, right? So they're going to be extremely interesting objects for a long time, but they are not the same thing as LIGO or CERN or the James Webb Telescope, because they do have this national security and potential for economic ramifications. So you can't treat them the same way. And to your application point, I don't think they'll be dead end. I mean, I've devoted my career to it. I think there'll be tremendous applications because simply having this ability to simulate quantum mechanics, a lot of the problems we try to solve with big computers are chemistry, material science. That's a huge, huge, huge market. There's going to be ramifications. What we don't know is when, okay? We don't know how big you need to beat the best classical approaches, because we have 100 years of really clever people figuring out tricks to calculate those same properties, and so we need to beat those. So that's one part. The last part of your question was, is it a coding problem or a hardware problem? And if you look at the whole problem, there's the physics of the qubits, there's the interconnect, there's the classical control, there's environmental control, there's the error correction, there's the programming languages, there's the mathematics and the algorithms. I think we've had tremendous advances in all of them over the last 20 years. I think the hardware of the integration has more, that's where the hard problems lie that are going to be dramatic. That's going to enable it. I don't know how much error correction there'll be left. I think there'll be more advances. I think there'll be more advances in algorithms. But I do think it's a hardware problem. And one of these approaches will work. It's just a matter of how long you beat on it, basically.
We'll take a question with the blue microphone in the back. Blue microphone, please stand up, tell us your name if you're a member, and ask a question.
Good evening. I'm here as a guest. My name is Rose. I have a question about materials, specifically why your team chose to use germanium. as opposed to other materials such as iron used in fusion-based superconductors.
Which type of superconductors?
Fusion-based, I believe they were a few slides back. There was a headline about them.
Okay. I'm mostly a quantum dot person in silicon. That's my main field. So most of my work is in spin-based quantum computing in silicon. I think that's a very promising approach. Germanium is interesting there. One of the main problems with silicon quantum computing is its indirect band gap, meaning it adds complexity to the dots. Germanium has holes. Holes are cool because they don't have this indirect band gap issue. They're in the valence band. So it's interesting material. On the other hand, we know way less about germanium than silicon. And if you see the heterostructure stack, we purposely designed it so the silicon was on the top and the bottom. The germanium is only in the middle because germanium is a bad material for some reasons, for oxides and so on. So the reason we're interested in it is because there's synergy with spin-based qubits, and there's a superconducting element. It's not necessarily because, and it's compatible with 300 millimeter wafers and modern processing. It's not necessarily because it's the best material in the world to do it. It's a very promising one. There's a lot of interesting science there. The superconductor is different. That could be aluminum, niobium. That's another question. There's a huge space of answers there, and we have nowhere near explored enough different types of superconductors to know which is the best. Tantalum is a new fad. There's a lot of different ones. There's a lot of choices, and it comes down to the interface, which is why we bought this MBE machine that can test a lot of different types.
Okay, I'm going to take one from YouTube, then we'll go to the red microphone, and then we'll go to the blue microphone. The question from YouTube comes from Neil in Colombia, South America. What do you think of Psi Quantum saying photonic quantum computers will be mass producible in existing semiconductor fabs by 2025-ish with hundreds of logical qubits? It's a kind of follow-up to earlier questions.
What can I say here? I mean, I don't like to select specific companies. I think there's a tremendous amount of VC money and coming into quantum computing. I think companies are under a lot of pressure to have results. I think this is a really hard problem. So I hope that they have one by 2025. I think it'll be really hard to field that.
So I think I said the red, but Bill Phillips has his hand up, and it might be a follow-up to the earlier question. So let me, if you will let me, I will call on Bill again. Oh, Bill?
You mentioned that one of the magic of quantum algorithms is to put the answer on the diagonal. In other words, to put the answer in what you are going to measure when you do projective measurements on the qubits. Now, what I'm wondering is, you could imagine a quantum algorithm, and I just don't know enough about this, where the answer is in the correlations. In other words, maybe you make Bell measurements on pairs or more qubits. Is there any future in trying to make algorithms like that?
I don't know exactly what you mean, but it sounds a lot like Shor's algorithm, right? Where you're finding the period of a function, and you're using math afterwards to actually find the answer. But you still, at the end of the day, have to extract something from something where you can extract from. What I alluded to in the first part of our talk was this measurement-based concept where if you do a lot of joint measurements, as you know probably, Bill, there's a lot of interesting measurement-induced phase transitions and things that happen. I think that could be an interesting new paradigm for computing, but it's still very early days, and we don't know how to do it. But amazing things happen. You get these induced quantum error correction kind of for free from doing a lot of joint measurements across your system, and maybe you can also drive dynamics that way. So I think it's a great question. I think there's a lot of research to know to actually map it to something useful.
Hi, I'm John Chernyavsky. I'm a member. My previous background was at National Science Foundation in both the Computer Science Directorate and the Education Directorate. And my last year at NSF before retirement was to work with the NSF representative on the OSTP quantum panel on education in particular, K-12 education initially, and then not so much, but undergraduate and graduate education. So I'd like to know what, it's been 2 years since I've been at NSF, and I'd like to know what sort of progress has been made there. I know we made some early awards to some of the education folks interested in kind of K-12, primarily high school education, on quantum information theory. I'd be interested to see what you're doing at the undergraduate level and at the graduate level. I know we had some things in the plans, but I haven't seen anything coming out of it yet.
Yeah, well, first of all, thank you for your service at NSF. I love NSF. I think there's been a good deal of progress, and maybe not fast enough for all of us. One, the Q2Work program was launched, which created the Q12 Consortium, and now we're 2 years in. We actually hosted World Quantum Day. We had hundreds of kits that went to high school teachers around the country, which taught various different approaches to teaching sort of core concepts of quantum, one sometimes via a game, sometimes via other little exercises. That was a pretty good success, and we're hoping next year it'll be much bigger. The other thing we've been thinking about a lot, and we've hosted a few workshops with other agencies, not NSF, but can you create senior undergraduate, early master's courses where people get a hands-on experience, open-ended, of doing research? So in other words, I give you a room and a fridge and some components, put you in a team and ask you to fix one piece of this problem or advance where the less team left off. Think of like the robotics competitions or things like that. Can you create an open-ended program where I can send, say, either a senior undergraduate who's great, or I can take an ASIC designer from my company or agency who's an amazing RF engineer, doesn't know any quantum lingo, send them there, work on that team. Maybe one other person's a physics major, another person's an EE major, and together they teach each other the quantum lingo, so that when he comes back in 8 weeks or 3 months or whatever it is, he's still a great RF engineer, but he kind of knows what this quantum stuff is about. He can speak the language, he can communicate with the physicist. I've seen that take 2 years, 3 years. If we could compress that down to 2 months, that would be a huge win for everybody. We're working on stuff like that.
Charlie, a great talk. I really resonate with your feeling that solid state devices are probably going to win out in the long run, and that doing stuff in silicon and germanium is a great direction to go, because there's a lot of solid stuff from the semiconductor industry around that. However, as you pointed out, classical digital, anything, but a third, 2/10, 1/10, it's a zero. So the very highly specialized semiconductor tools now are sloppy. They do not have good relative precision, and you need small things. To be self-serving, I'm working on a really highly precise lithography technique. Michelle Simmons uses it to make the donor spin qubits of her type, but I think it has great value in, for instance, we could make nano imprint templates that are way more accurate than any other. Wherever this goes, I think we're going to need better tooling, better fabrication tools with much higher precision in order to make solid-state qubits really viable, to cut down the amount of error correction that we need to do. Is the government going to think about funding some of the tool sets? You've already done some of that. Thank you very much for that. But we could use some more help.
So you're talking about is yield. Like if we need a lot of devices, they got to work. And what we mean by yield for quantum devices may be very different from what we mean by yield in transistors. Right, so this is a great question because it lets me talk about something that's a little bit outside quantum, which is the CHIPS Act, which is a policy, it's an act in Congress that's been debated for, seems like 100 years now, of whether to fund U.S. manufacturing of advanced node lithography. It's about $50 billion, $52 billion. We're waiting to hear whether it passes. But in that act is around $5 to $10 billion for packaging and a national semiconductor technology center. And the debate around what that NSTC should be includes emerging technologies like quantum. Do you want it to be more about the next node of digital logic, or do you want components of exotic new technologies like photonics, memristors, neuromorphic, quantum computing? And that might mean very different. So we're very much in that conversation because we want to make sure that there's a US capability to make exotic things. Even putting a superconductor in a fab is not a trivial thing right now, because the whole point of your chip is to make everything perfect as possible. If it's not on the list, it's not going to go in. So you need different types of fabs that are willing to try different things, and you need ways to prototype that, and you need a cadre of people who can help you. That's the ideal scenario, and we'll see how the policy and the actual implementation, if it passes, pans out. But definitely thinking about it, working on it.
Okay, we're going to go to Carl Merrill on Zoom. Carl?
Thank you. I enjoyed your talk. This is an area that I'm more of an observer in, although I started working with computers in 1953, the great brass brain at Washington that used gears to add and subtract sine waves. But the real question I have is an article I saw in Nature that appeared yesterday on the use of boson sampling. And they claimed that they had the equivalent of a 216 qubit device. It was nodes, actually. And in 36 microseconds, they did a set of tasks that would have taken 9,000 years with a regular computer. And this apparently is a collaboration between NIST in Colorado and Xanadu in Canada. And it sounds like a whole different way of approaching this. And I just wondered, I'm sure you must know all about this, and I'd like to have your opinion. And is this really a totally new way to do this, and how revolutionary is it?
Sure, I can tell you what I know. I'm not a complete expert in photonic-based quantum computing. There's a few companies, PsiQuantum was mentioned earlier, Xanadu, which are pursuing photonic-based approaches. Photons are especially interesting because they don't like to talk to each other at all. So you need to come up with clever ways to do the computation. It's usually done by this kind of measurement-based approach. Actually, that inspired some of the work we did here on measurement-based gates. Their fusion-based approach to quantum computing at PsiQuantum. At Xanadu, they're pursuing, as they've stated as an end goal, a fault-tolerant quantum computer based on which are called GKP states and measurement-based quantum computing. In this paper that they came out with yesterday, and I haven't read it in detail, I apologize. They're trying to do Gaussian boson sampling. So we know that fault-tolerant quantum computers are non-Turing complete, meaning you can't simulate them on a classical computer, right? But they're hard to build. So people started coming up with other problems, which also seem to be hard to simulate, but are not quite quantum computers. That's called boson sampling. It was proposed by Scott Aronson. Gaussian boson sampling, I think, is even a step below that. It's not quite. I don't want to say anything that's wrong, but it's not quite boson sampling. So I don't know yet whether it's a fair comparison to compare it to the classical 9,000 hours. I'll tell you that, and I think one of the things we've been seeing, and this happened with the Google experiment, is they came up with a contrived problem called quantum supremacy, which is basically running a random circuit. And running a random circuit on a quantum computer actually seems to be hard to simulate. So if you compared it at the time, it took them whatever it was, seconds or minutes to solve it. If you ran it on Titan, the biggest supercomputer we had at the time at Oak Ridge, it took a month or whatever. The problem is the Titan supercomputer gives you all the answers. It solves the whole thing. Whereas the simulator is it's sampling a distribution. So people have applied tricks to make the actual calculation more efficient, and it cuts down the lead over time. Now, the counter to that is for a fault-tolerant quantum computer, every time you add a qubit, you double the size of the system. So if you just went from 50 to 60, no way in hell you're ever going to simulate it. So it's very quickly, if you can make your qubits better as you make the thing bigger, it's going to be hard to simulate, that's for sure. It doesn't mean it's useful in any way, right? It just means that it's hard to simulate. So there's hope that it's going to be useful, but it doesn't mean it's actually a useful problem. This boson sampling thing is extremely cool experiment. I mean, it's amazing. It uses squeeze states. It's really cool. What's nice about it is it uses time as a sort of multiplexer to increase the size of the computer. But I think that there are still questions out there about what is the fair comparison to classical computing, and how will this scale with size, and is it ever going to be really useful for anything important? But I think it's a tremendously interesting scientific problem, and they've made a lot of progress technologically. And photons are a great example of this race of technologies, because 5 years ago, they were left for dead. You know, nobody knew how to do a 2-qubit gate without a huge overhead, and some companies went out and tried to do it, and they've made tremendous progress where it doesn't seem impossible anymore. It just seems really hard, really hard. And we've seen on other technologies too, that they're left for dead and they suddenly come back with a new idea, and then they're left for dead and they suddenly come back. You know, so it just goes to show you that you don't want to put all your eggs in one basket because we're not there yet. We don't know which is going to win. So that's my answer.
Yes, red microphone, Tim.
Timothy Thomas from a member of the society, and thank you for a stimulating talk. I want to ask about one little phrase in it, entanglement by measurement. What could that mean?
Oh, sure. So let's say you have 2 qubits, 0, they could be in any state, but let's just say they're in 0 and 1, 0 and 1. Okay, if I could measure them both at the same time, the end state might be a singlet, which is an entangled state. So when we say entangled, all it really means is I can't describe them separately anymore. I need to use that whole matrix, right? So you can come up with a system, say if these 2 qubits are coupled to the same resonator, where you do the measurement and the end state is not individual qubits, but it's a singlet state or a ground state that's entangled. And that's all we mean. And so when you turn off the measurement, you turn off the coupling, and they're left in this entangled state. That's all it means. But there's some probability of ending up there or somewhere else. You know.
I'm Bob Hershey. I'm a member. What do you consider the high water mark in what's been done so far?
Oh, it's a hard question, actually. There's a tremendous amount of stuff. You know, and if you're been funding this field or working this field for 20 years, it feels like this slow, painstaking scraping of progress. But there's been a few, I think, really cool results. The transmon qubit. For a long time, superconducting qubits, you think of them as a washer, right? Left is 0, 1 is counterclockwise. People didn't know if they were coherent for a long time, because the way to read it out was by a squid, another superconducting qubit that would detect, is it clockwise or counterclockwise rotation of current. And the visibility was like 50%. Like when you measured it, you could only tell like 50% of the time whether it was left or right. So people argued incessantly about whether these things were even quantum. Like, was there superposition there at all? Until circuit QED and transmon, because in circuit QED, you use microwave photons to read out the qubit. You put a transmission line next to it, you couple it very weakly to the qubit, and 99% visibility comes out the other end. So you clearly see what are called Ramsey fringes or Rabi oscillations of the qubit going from 0 to 1. And it's like, it's quantum. There's no argument. I mean, actually, there's still arguments. You know, we still have people working on it, even in my lab. How quantum is it? But God, when you see that picture, it's quantum. The quantum dot, when you first did readout of a single spin, I mean, a single spin, a magnetic wave of a single spin is incredibly small. People cannot read that out. You know, like, just the concept of being able to read it out. So the first time you did measurement and it worked, that was the amazing part. The Google experiment and these supremacy experiments are also quite amazing. I mean, they're the first demonstration of 50 quantum devices working, kind of. Like, you can calibrate them. I mean, there was a lot of arguments at the beginning of this field of whether quantum mechanics would start to fall apart at something like 200 qubits. And so far, quantum mechanics is still working. So like, those are just a few examples, but there are things like that where like, oh, should have done that 10 years ago. But a lot of it is hard fought progress, which is something I think people are starting to realize now that have started to invest in this. It's like, it's just hard work.
Hello, I'm Chris. I'm a guest. Thank you for having me, and excellent presentation. Thank you so much. Going through it and just looking at some of the stuff that you're presenting, you mentioned, it's a two-part question. You mentioned how you only see visibility at the end if something's a 1 or 0. I want to know, if you only see the visibility at the end, how are you able to detect the error percentage, since there's so much variability? And then the other part of the question is, as you add on more qubits, and since it's analog and variable and that kind of stuff, how do you handle with the error rates, and how do you kind of prevent, because there's so many different combinations that can happen after that, how do you handle that?
Yeah, you just asked the two fundamental questions of quantum computing that for the first 10 years of its existence, we got every single time. Number one, it's an analog computer. Analog computers never work. Quantum computers won't work. Number two, how does quantum error correction work? And they're actually related. And this is the miraculous. This is how it works. First, quantum mechanics is linear, and so errors add additively. They don't multiply. And it turns out that every single qubit error can be described by 3 possible things that can happen to it. 1, nothing can happen to it. 4 things. 1, nothing can happen to it. 2, a bit flip error can happen. It could go from 0 to 1. 3, a phase flip could happen. It could go from I to minus I. And 4, it could do a bit flip and a phase flip. So those 4 error channels, if you add them together, describe any possible error that happens. And what error correction does is it solves only those 4 errors. And if you can solve all 4, any linear superposition, because quantum mechanics is linear, quantum mechanics didn't have to be linear, just the way the universe works. Because quantum mechanics is linear, solving those 4 solves every possible combination, even if it's like 0.00001. So that's the first thing, that quantum computers with error correction are digital, even though the qubits are analog, which is a miracle like, that's the most amazing thing in quantum mechanics. And Peter Shor also discovered that. Like, he did 2 amazing things. He first found the first killer app, and he predicted quantum error correction. So how does quantum error correction work? Because I just told you before that you can't copy a quantum state. There's no fan out, because as soon as you measure it, you lost the coherence. It turns out what you can do is you can take your qubits and you can introduce an ancilla, a 3rd or 4th qubit, and couple that weakly to you could do a CNOT gate, and you can measure that one without screwing up the information encoded in the others. So you can kind of do majority voting. You say, I took my 3 qubits and I encode that into a new state where if 2 of them are up, I'll call it the whole thing up. And I don't measure those 3 qubits. Those are still my quantum computer, but I can do an ancilla, and I do a CNOT gate of all 3, and then measure that. And it will tell me if there was an error on those one of the 3, but it won't screw up the state. And so then I can come in and fix that one without ever disturbing it. And that's another miracle of quantum error correction. Because at the very beginning of quantum computing, like in the 80s, early 90s, people were like, wow, this is a really cool thing for nerds and weirdos to think about. But then quantum error, because how are you going to correct this? It's analog, and you can't correct phase flips and bit flips. But then error correction suddenly made it possible. So that's the answer. Like, it's the most important question in quantum computing.
So I think we'll have just 2 more questions.
Bryce Eldridge, member. So how useful are advances in superconductivity at near room temperature to solving some of the technology problems for quantum computing?
To first order, not at all. There is hope. People have thought about, well, can I use high TC superconductors to make qubits, and people have played around with it. It turns out that those systems, which tends to be like these ceramics, these weird systems, don't seem to be good for coherence. And even like different types of type 1, type 2 superconductors at cold temperatures, some are better than others because some are more privy to quasi-particles or Cooper pairs breaking up. So we don't know is the answer. Like we spent all the material science just trying to get them to work at 50 millikelvin. And the next step in one of our problems is like, can you get it to work at 2 Kelvin or 4 Kelvin? And then, maybe 100 years from now, worry about room temperature superconductivity if it's ever discovered. Where it could make a difference is for the cabling. If you want to put your electronics at 77K, if you had a good cable that went all the way down with low loss, that would be very interesting. So it comes into play there.
I wanted to ask you a question regarding, you said that you're pushing for a $1 billion funding. Is that on a yearly basis? Over how many years? If it's $1 billion, for how many years per billion?
It's just, if you add up right now,
right.
You get about 900 million is what you get for our NQI funding, all the quantum funding in the U.S.
Right.
That's what we spend now, pretty much.
Right.
In the government only.
Right. So you want to push for a little bit more? Right?
No. Well, yes. Always want to push for more.
Yeah. Well, no.
But because, by year.
Because for 5 years, $1 billion per year. So as a thought, if one goes retroactively and look how much money has been spent from the 80s, from the time the Japanese, raised the flag was raised that the Japan is going to take over these years, from the 70s to today, that we have achieved exascale computing, it may be worth the exercise how much money was spent, adjusted for inflation, and maybe make an argument that you need something that is comparable, because $1 billion, and we worked off in the federal government.
Billion's not what it used to be.
It's schizophrenic. On one hand, 100,000 is a lot of money from your own pocket.
I'm with you.
And it goes very quickly. So $1 billion is not very much. And how much is Europe? I mean, EU also is putting a lot of money. I used to track this.
Question I get a lot. It's actually kind of hard to compare because everybody publishes numbers like either as 10-year funding or one, like it's all apples to oranges. I think Europe is spending roughly comparable to what we are.
And
they have a more complicated system because they have the EU and the member states and so on.
Yes.
But the one thing we consider an ecosystem, and the U.S. industry is spending a lot of money. And that's where a lot of billions are coming from.
I think I'll close with a competitiveness question. So I know in quantum communication there's a group in Austria that's the Zellinger group that does a lot of really, really interesting stuff. And the Chinese have an active program in quantum communication. I haven't read a whole lot about what the Austrians or the Chinese are doing in quantum computing. I'm sure the Chinese are busy. Could you comment a little bit on what is going on in some of the leaders in the world, like the Austrians and the Chinese?
In quantum computing or everything?
In quantum computing.
Could be here a lot longer.
Just quantum computing.
I think there's a lot of strong quantum computing groups around the world, and it's one of our 6 pillars, international cooperation. And I think it's important to remember that quantum has always been global. These original ideas about quantum computers came from David Deutsch in England. A lot of the foundational AMO work came from Europe. So a lot of this has always been a global field, helping each other. In China specifically, there's some strong groups. Alibaba has published interesting papers. USTC, one of the leading Chinese universities, have pretty much replicated the Google experiment, the 50 qubit now to 60 with better fidelities. So there's a lot of fast progress here, and there's international competition, coopetition or whatever you say, because a lot of the Google, some of the former postdocs from UCSB have gone to China to start groups, like that happens in science and technology all the time. So it definitely is, people are trying to go as fast as they can. And the Chinese in particular have invested in superconducting qubits, photonic qubits. They have some very strong groups there and other places. But they're also insisting in networking and sensors. So it's a big world.
Are they going to break your NSA keys anytime soon?
I don't think they're going to do it anytime soon. But I think I told you why it's hard to build a quantum computer.
I know.
But I said you have to worry now, because when you think about 20 to 50 year time frames, which is how we protect information. Think about the plans to a nuclear weapon from the 1940s. You still would not want to find on the internet, right? So when you think about 50-year time frames, which is way cryptologists think, you have to be conservative, because two reasons. One, Moore's law is ending, so it's a kind of a whole wild west, as somebody said. You don't know what the new computational paradigm is going to be. And three, because we want to protect information for a long time, so it behooves us to be safe.
Well, thank you very, very much for very engaging
Thank you very
and
much.
stimulating talk. So thank you very much. And before you go, we have a few closing announcements. I'm planning for the next meeting to be in person, but ultimately that will be determined based on COVID and COVID-related measures in place in 2 weeks. The speaker on June 17th at our next meeting, which will be the 2,461st meeting, will be Sobita Satyapal. She is a professor of physics and astronomy at George Mason University, and she will be speaking about supermassive black holes. And that will close out the spring lecture series. The fall lecture series will begin with our meeting number 2,462 on September 9th. The speaker will be Drew Weissman of the University of Pennsylvania, and his topic will be technologies required to make mRNA vaccines, in particular the chemical modifications that he was involved in developing that allowed the development of the mRNA vaccines that probably all of us have somewhere in our arms and from the rest of our bodies. Please check the PSW website often for up-to-date information. Meetings and whether lectures will be in person or via Zoom. COVID and COVID-related public health measures constantly changing, and PSW is adjusting plans accordingly. Please join us for these meetings, and also please note a new feature on the website. You can subscribe to the PSW calendar for automatic updates to the schedule as they become available. Just click on the calendar icon on the PSW homepage. And finally, let's thank those who helped produce tonight's event. Robin Taylor, our executive director and empress of all, who runs the video, the live stream, and the Zoom, and who worked very hard to get all this equipment ready before we got here, and then made sure it was all set up after we got here. So please, let's all thank her. James Heelan, our recording secretary, who prepared the minutes and read them for us. Mark Clampin, who's ably run the soundboard tonight. Thank you, Mark. Brett Magarum, who did check-in and room management. And our camera people, Robert Thompson and Jared McQueen. And mic runners, I'm not going to remember. It was Lloyd Mitchell and Brett Magarum, and I thank you very much for doing that. And with that, I will now adjourn the 2,460th meeting of the Society to the social hour. We actually have refreshments after more than 2 years. I wish everyone a good morning, afternoon, evening, or night, wherever you may be. Meeting is adjourned.